Hello and welcome to Eternity Tutorials. Today I'll be dealing with real numbers. We need to learn about the number system. The whole number system is right in front of your screens. If you see, this is natural numbers, which we all know starts with 1, 2, 3 and so on up to infinity. We have whole numbers which starts with 0. The integers which has negative as well as the positive numbers in it. And then comes the rational numbers. Rational numbers are in the form of P by Q, that is numerator upon the denominator, where denominator is not equal to 0. The few examples of each type of number is given to you. We have irrational numbers and few examples are given here like root 2, pi, 2.71828182846 and so on. The whole system together is known as real numbers. Now I will tell you about Euclid's division lemma. Euclid's division lemma states, given two integers a and b, there exists a unique integer q and r such that a is equal to bq plus r, where r is between 0 and b. Let us understand this lemma. If you all remember, in your previous classes you've done dividend is equal to divisor into quotient plus remainder. So if you compare these two, they are exactly the same. The dividend becomes A, divisor becomes B, quotient becomes Q and remainder becomes R. Let me take a very small example to explain you. If I have 8 which is being divided by 3, then we all know that this is the division. And this can be written as 8 equal to 3 into 2 plus 2. We are doing exactly the same thing in the division lemma. A here is 8, B is 3, Q is the quotient 2 and R is the remainder 2. Now let us come to this part which says 0 is less than equal to R is less than B. See that R is the remainder. So when do you stop the division? Either R has to be 0 or R is less than the divisor. Please see, that is B. This remainder 2. When this is less than 3, then we stop to the division. Or if it would have been 0, at that time we would stop the division. So basically all the remainders, they are either 0, more than 0 or less than the divisor, that is 3 in this case. I will now take an example to explain the division lemma in details. Let me take the example of 455 and 42. We use the Euclid's division lemma to find the HCF, that is the highest common factor, using Euclid's division lemma. How do we use division lemma? We write the bigger number here, the smaller number out of the two here, into something, and which will give me a remainder. That means I multiply 42 by some numbers so that we have a remainder, or we may not have remainder. I multiply 42 by 10, the remainder comes out to be 35. Now here I write down 42. This number comes here and the remainder comes this side, into 1 plus 7. Now this 35 again will be written here and the remainder comes here into 5 plus 0. And this number is the HCF. I will explain you this example in another way, as we all are aware how to find the HCF by division method. We write 455 here and 42 here. I write down 10 and I get 42 3 5 0 0 3 5. This is the division that we have done for 455 divided by 42. This is the quotient. So we write 455 here as 42 into 10 plus the remainder 35. Now to find out the HCF, we make this divided by, now we take 42 divided by 35. When I divide this, I take 1, 35, the remainder is 7. Now see, 42 here has been written as 35 into the quotient 1 plus the remainder 7. I divide again. I take 35 here, 5, 35 and the remainder is 0. And we say that this is the HCF. So here again we write down that 35 is written as 7 into the quotient 5 plus the remainder 0. And we say 7 is the HCF. Now we take another example. The question is then find the HCF of 135 and 225. Now before I take out the HCF by Euclid's division lemma, I find out the HCF by the normal division method. Now I divide it. I get 135, 0 and 9. I take 135 here, again 1, 90, 45, 90. Now this division method will be done in your rough work, and as the question is given to you, we apply the Euclid's division lemma. I write down the bigger number, 225 is equal to, as you see from the division, it is 135 into 1 plus 90. Now I write down 135 here and 90 comes here into 1 plus the remainder is 45. As you can see, I am only writing this division in the form of the Euclid's division lemma. Now I write down 90 is equal to 45 into 2 plus 0, and this will always go on unless you get 0. So here 45 becomes the HCF. Now let me take another application of Euclid's division lemma. I write down a question. Which says, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Now how do we solve this? As we have gone through the Euclid's division lemma, it says that A is equal to BQ plus R, where R lies between 0 and B. So in this case, if I take B to be 6, as you can see in the question, it is 6Q plus 1. So instead of B it is 6, and instead of R it is 1 in this case, 3 in this case, and 5 in this case. So if I take B to be 6, let me say let B is equal to 6, then R will be from 0 to 6, that is this. That means R can take any value as 0, 1, 2, 3, 4 and 5. So the numbers here, A is 6Q. Another case of A would be 6Q plus 1, then 6Q plus 2, 6Q plus 3, 6Q plus 4, and the last one being 6Q plus 5. Now if you see 6Q, we have to show that out of all these cases, which case is the odd integer. That means which is not divisible by 2. If I see 6Q, I can write it as 2 into 3Q. This is divisible by 2 as we are getting 2 into something. So we say that this is even. Now if you see here, we have plus 1. That is, I can write it as 2 into 3Q plus 1. This is divisible by 2, but plus 1 shows that we have a remainder, which shows that this is not divisible by 2 and hence it is odd. Now here, I again write down, I take 2 common and I get 3Q plus 1. That means again I can write it in the form 2 into something. That means it is divisible by 2 and hence it is even as we do not have any remainder. Here I cannot write it as 2 into something, but I have 2 into 3Q plus the remainder 3, because again we have the remainder, so we have it is odd. This can be written as 2 into 3Q plus 2. Again there is no remainder and it is written as 2 into something, so we get this to be even. Here I have again 2 into 3Q plus 5. Again I have a remainder as 5, which shows that this is odd. Now if you see, out of all these cases, I've got 3 cases, number 1, 2 and 3, where the numbers were odd. That means 6Q plus 1, 6Q plus 3 and 6Q plus 5. They are odd integers, and that is what we wanted to prove. Let me take another similar example so that it becomes more clear to you. Now it says use Euclid's division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Okay, now please see, you need 3m and 3m plus 1. That is 3 into something. So here again we consider b to be 3. If b is 3, then r, the remainder, lies between 0 and 3. That means r can take the value as 0, 1 and 2. Now a is equal to bq plus r by Euclid's division lemma. Now I take the first case where a is equal to 3q plus 0 when the remainder is 0. So this is equal to 3q. Because we have to find the square, so I square it. I get a square is equal to 9q square. This can be written as 3 into 3q square. Why I'm writing in this case? Because I need the form 3 into something. So I've taken 3 out and I've written 3q square inside. Now this can be written in the form of 3m, where m becomes equal to 3q square. I repeat, I have found the square because the question deals with the square of any positive integer. Now 9q square can be written as 3 into 3q square because we need 3m. So 3 into something. So this something I've taken to be m, and m is equal to 3q square. This I've got the form of 3m as in the question. Now I take case 2 where the remainder is 1. Now I square it. When I square this a square, I get 3q plus 1 whole square. I apply the formula for a plus b whole square, which is 9q square plus 1 plus 6q. Now I need the form 3m plus 1. I rearrange the terms. I get 9q square plus 6q plus 1. Now here I take 3 common out of the first two terms, and I get 3q square plus 2q plus 1 remains as it is. Now I write it as 3m plus 1. In this case m is equal to 3q square plus 2q. Please see, I have tried to convert it into the form 3m plus 1. Here m was 3q square plus 2q. Now I take the third case where a is equal to 3q plus 2. Again I square it, so I get 3q plus 2 whole square. When you square this, I get 9q square plus 12q plus 4. In this again, I take 3 common out of the first two terms. So I get 3q square plus 4q plus 4 remains as it is. This can be written as it is, and 4 can be written as 3 plus 1. Now out of the first two terms, first term and the second term 3, I take 3 common. So I am left with 3q square plus 4q plus 1 plus 1. Now if you see, I can write it as 3m plus 1, where m is equal to, in this case, m is 3q square plus 4q plus 1. Now, another question will be dealing with the cube. So I say use Euclids division lemma to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8, where m is some integer. Now because we have to take the cube, so that doesn't mean that I will take b to be 9, because the cube of 9 will be very big. So here I take b to be 3. Again, if b is 3, then r lies between 0 and 3, which shows that r is either 0, 1 or 2. I take the first case where a is equal to 3q plus 0. Now I take the cube of it. The cube of 3q is 27q cube. This can be written as 9 into 3q cube. I've taken 9 out because I need the form as 9m, 9m plus 1 and 9m plus 8. So this can be written as 9m, where m is equal to 3q cube. I take the next case where a is equal to 3q plus 1. I cube both the sides and I get 3q plus 1 whole cube. This is equal to 27q cube plus 1 plus 3q square, that is 9q into 3, 27q square plus 3 into 3, 9q. I rearrange the terms here and I get 27q cube plus 27q square plus 9q plus 1. Now I take 9 common out of the first 3 terms. So I get 3q cube plus 3q square plus q plus 1. This can be written in the form 9m plus 1, where m is equal to 3q cube plus 3q square plus q. I take the third case, 3q plus 2. I take the cube of this, which is 3q plus 2 whole cube. So the cube comes out to be 27q cube plus 36q plus 54q square plus 8. I take 9 common out of the first 3 terms again and I get 3q cube plus 4q plus 6q square plus 8 remains as it is. Now this can be written again in the form of 9m plus 8, where m is equal to 3qq plus 6q square plus 4q. All this includes the first exercise of your real numbers. If any one of you has any doubts, you can write the doubt in the comment section and I will revert back to you. Thank you.